everyone, and welcome to our walkthrough through our workbook on measures of association. Let's go! As we've already seen, evaluating the relationship between variables is at the heart of data mining. As we step into the actual math behind everything, we have a number of techniques that we can use. The first one is distance calculations like Euclidean, Manhattan, and cosine similarity. And then we have measures of independence like chi-square, covariance, and correlation. And lastly, we have predictive measures like regression and ANOVA, which we will explore in another workbook. So here, we're going to talk about distance, we're going to talk about cosine similarity, chi-square, and correlation. In order to do this, we're going to work with our adult dataset again, and we're loading our libraries and the dataset just like last time, but we are going to add some of the libraries because we're working with some more involved math. The first library that we're going to work with is scikit-learn, and we're going to use the cosine similarity function from the scikit-learn metrics module. We're also going to use SciPy, which is NumPy's big sister for advanced math, and we're going to use the math package as well because we're going to do some advanced math calculations. So this is what the libraries look like. You're seeing we're going to work with cosine and with degrees because cosine similarity, right? And we're going to read in our adult data set, just like we did before, and we're going to verify that we can see the data. So let's do that. And here we are. So let's start with our section on distance and with a case study. Let's say you want to buy a car, and not just any car, but you want to buy a car that's as close to this one here in the picture as it can get. This here is a red 2020 Mercedes, but you have a budget of less than $5,000. So you go through 3 dealers. Dealer number 1 has a red 2012 Audi for $4,500. Dealer number 2 has a silver 2008 Mercedes for $8,000. And dealer number 3 has a red 2020 Chevrolet for $4,999. So now which car are you going to buy? Now we're going to use distance, and we're going to explain distance in terms of difference with a simple Boolean algorithm to find out which car we should buy. So for color, let's first talk about color. We're looking obviously for a red car. We're seeing that dealer number 1 has a red car, dealer number 2 has a silver car, dealer number 3 has a red car. So since the distance between red and red is 0, dealer number 1 and dealer number 3 get a 0 for red. Dealer number 2 get a 1 for silver because silver is different from red. Now let's talk about the year. We have 2012, 2008, and 2020. So dealer number 1 gets 1 point for 2012 because 2012 is different from 2020. There is a distance. The same goes for dealer number 2 because 2008 is different from 2020. However, dealer number 3 gets 0 points because there is no distance between 2020 and 2020. So now let's move on to the make. We have Audi, Mercedes, and Chevrolet. You guessed it, dealers 1 and 3 each get a 1 because Audi and Chevrolet are different from Mercedes. However, dealer number 2 gets a 0 because Mercedes is the same as Mercedes, so there is no distance between the two. And finally, let's talk about the price range. We're looking for a car for less than $5,000. In which case, here dealer number 1 and dealer number 3 both get 0 because both of these prices are less than $5,000. However, dealer number 2 gets a 1 because there's a clear difference between $8,000 and $5,000. So now that we have all our 1s and 0s in place, let's total them up. Dealer number 1 gets 2 points because the year and the make are different, but the color and the price are are within what we had imagined. Dealer number 2 gets 3 points because the color is not right, the year is not right, and the price is not right. So that's 3 points. However, the make is correct. And dealer number 3 gets, you guessed it, 1 point because we are looking for a red car, we're looking for a 2020 car, we are looking for, well, a Mercedes. So this is a Chevrolet, there is a 1, but we're looking for a car that's for less than $5,000. This car is less than $5,000. So the distance is smallest between dealer number 3, the car from dealer number 3, and the car that we had been looking for. And the distance is largest between dealer number 2 and the car that we had been looking for, even though dealer number 2 offers a Mercedes. So if we are looking at distance or difference in order to help us decide which car to purchase, then we would clearly go with the red 2020 Chevrolet for $4,999 from dealer number 3. In other words, the closer 2 data points are, or 2 data series, the smaller the distance is between the 2. This is very, very important. Now, as you can tell, we're going to talk about 3 different kinds of distance. We're talking about Euclidean distance, Manhattan distance, and cosine similarity, all of which are being used in algorithms going forward. So let's have a little trigonometry moment, shall we? Because when we talk about distance, we're essentially talking about triangles. When we talk about Euclidean distance, we talk about the direct path from point A to point B here, and that is typically a diagonal path. When we talk about Manhattan distance, we talk about a path that involves a right angle. That's a city block distance as well. So in the shape of a triangle, D here would be the Euclidean distance, and these 2 sides here would be the Manhattan distance between point x1, y1 and point x2, y2. And whenever we work with triangles, of course, we work with the Pythagorean theorem. So if we solve the Pythagorean theorem for D, then D equals the square root of this side here squared, that's x2 minus x1 squared, plus this side here squared, that's y2 minus y1. And that's what we're seeing here. So D equals the square root of this side squared plus this side squared. And that is the formula for Euclidean distance. So how does this work in Python? Let's first program the actual straightforward math. For that, we're going to set up 2 series. That's 2 vectors, x and y. My x vector is 1, 2, 3, 4, 5. My y vector is 6, 7, 8, 9, and 10. So we're going to double check what these 2 series here, these 2 vectors contain. And we see they're in 64 data type. And index here is 0, 1, 2, 3, 4. Value is 1, 2, 3, 4, 5. Index of series number 2 is 0, 1, 2, 3, 4. And the values are 6, 7, 8, 9, 10. Looks legit. All right, so now we can start setting up the Euclidean distance formula. The first thing we need to do is we need to square each data point in our x series, and then we need to square each data point in our y series here. Let's do that. We are going to give the data points in our x series the variable a, and in our y series we're going to give our data points the variable b. That's what we're seeing here, a and b, right? So we're going to use the variables p1 and p2 here to store our arrays or to store our series in. And we're using our numpy.sum function here. Here is where we are squaring our values for each of our vectors here. So then we can build the formula with the squared values. And here's our square root. This square root is this square root right here. And then we are going to create the sum of our a minus b, because remember, a minus b, right? Multiplied by a minus b, because that, again, is the square. That's exactly what we have here. And then we are going to do this for both a and for b in the zip, that's the iterative series x and y. So that way we have the x's covered and we have the y's covered. Good, and that gives us our Euclidean distance. And we are seeing here the Euclidean distance between our two series, or two vectors, is 11.180, and so on and so on. Yeah, that makes sense mathematically. It replicates our function here that was derived from the Pythagorean theorem for our Euclidean distance, d. Very nice, but can we do this more easily, because this seems to be a little maybe convoluted to you? So another way of achieving the same thing is to use the dot product between two arrays. Dot product is going to eventually lead us towards cosine similarity, which is why we're looking at it here already. Good, we have the same thing. We have our point 1, our point 2, same kind of series, only that this time we're setting these up as numpy arrays. And we see here that the first array is our 1, 2, 3, 4, 5, and the second array is our 6, 7, 8, 9, 10. And these arrays are basically the same as the series up here, only in array format. The next thing we're going to do for our formula is to subtract point 2 from point 1, which replicates this here, where our x1 is our point 2, our x2 is our point 1, but we're seeing here we are subtracting x1 from x2 and y1 from y2, and our x's are stored in point 1, our y's are stored in point 2. We're going to store this relationship in our temp variable. The next thing that we're doing is to find the sum of squares. The sum of squares, because here are the squares and here's the sum. So we're finding the sum of squares between our point 1 and our point 2 arrays that we've set up here. And we've already stored this relationship in our temp variable. So what we need to do now is we have set our arrays up side by side here. All we need to do is take the dot product. That means item 1 in point 1 times item 1 in point 2. Then item 2 in point 1 times item 2 in point 2, and so on and so on. And we're going to cycle through our temp lineup between point 1 minus point 2, and we're going to apply this to each of the rows in our temp variable. That gives us the Euclidean distance between our two arrays, and of course we still have to apply to that our square root, because all we've done so far is this. And now we need to apply this. So the square root of the sum of squares, that gives us the Euclidean distance. And what we're seeing here is, of course, that the Euclidean distance, when we calculate it this way, is exactly the same as when we calculate it with just the plain math. All right, now let's apply what we know to the adult data set. The question that we need to solve is, does income USD depend more on a person's age or on their education years? So what we need to calculate is the distance between income USD and a person's age, and the distance between income USD and education years. Then we compare these two distances and we find out which distance is shorter. The shorter distance means that the attributes are more closely related. Let's get started. We're going to set up our NumPy arrays as we did before with our dot product calculation. Here, adult age and adult income USD. And then I've already done this here. We're checking the arrays for point 1 and for point 2. I'm going to do this again. So now we're going to solve what we have solved here with a lot of math with one line. We're going to say what our distance is, and we're going to use our linear algebra function in NumPy, and we're going to use the matrix or the vector norm here because we have in fact set up these two vectors here, right? These two arrays. So we can easily just subtract the second vector here from the first vector. Of course, the result is being stored in our dist variable here, and then we can just print the contents of our dist variable in our output. So we're seeing that the Euclidean distance between age and income USD is, and then this number. Now your job is to do exactly the same thing, but not between adult age and adult income USD, but between adult education years and income USD, and then to compare the output of the Euclidean distance. Wherever you see the smaller number, this is where you will find the two attributes more closely related than the other attribute with income USD. I'm giving you the option of using either the one-liner here of linear algebra, or if you would like to use the dot product, then please use the dot product. It doesn't matter, you should see the same results either way. And that completes our conversation about Euclidean distance. So now we're going to talk about Manhattan distance. Manhattan distance is also called the rectilinear distance, so we're not using the hypotenuse d to get from our point 1 to point 2, but we're going to use our right angle sides here. For that, we could do traditional math, or we could apply our data mining libraries, and of course, we're going to do just that. We're going to use our SciPy library, and from our SciPy library, we're using the spatial distance function, which we're going to import as dist. Our setup is the same as before. We need to convert our arrays into our point 1 and our point 2 variables as our sample data. But then we're going to do this very quickly in one fell swoop. We're going to print our Manhattan distance as dist here. And if we look at our dist function, we see that we have a whole lot of different distance calculations at our disposal. not just our city block distance, which is our Manhattan distance that we're going to use, but we also have correlation at our disposal. We have cosine as the cosine distance. We also have the Euclidean distance and a whole lot of others. So that makes things very convenient for us. Here we're going to use dist.city block between point 1 and point 2. That is 25. That was quick, wasn't it? And we can do the same thing with the Euclidean distance. If we pick not dist.city block, but we pick dist.Euclidean. And again, we get our Euclidean distance of 11.1803, and not surprisingly, that's the same as up here and as up here. All right, so that is Manhattan distance, very quick in one line. Let's do this with the adult data set. We're going to do exactly the same setup here. We're going to set up our point 1 and our point 2, adult age and adult income USD. And then we use our one line to print with the distance.city block point 1 to point 2. And we get our Manhattan distance between age and income USD right here. So now, as before, I'm going to ask you to calculate the Manhattan distance not between age and income USD, but between education years and income USD. And remember, the smaller the distance is between 2 points, the more similar, the more related are our attributes. So now it should be easy for you to compare the outcome from your calculation between education years and income USD, also for the Manhattan distance, to tell me whether age or education years is more related to someone's income. So now, talking about our triangle, we have so far looked at our Euclidean distance and we have looked at our Manhattan distance. The next thing we're going to look at is our angles. Angles between two different vectors. And this is where cosine similarity comes in. The cosine similarity is related to the dot product that we're going to have to calculate between two vectors. And then we're going to calculate the cosine of the angle between those two vectors. So very quickly, the cosine of 0 degrees is 1, and the cosine is 0 for a 90-degree angle. And are we going to do this by hand? Well, we're going to do one little example by hand, and then we're going to rely on our functions that we already have. As before, when we compare vectors, when we compare arrays, we have to set up our arrays here. I have a little one here between 1, 2, 3 and 1, 1, 4. So these are my little vectors that I'm going to compare. First, we're going to do this manually with a dot product that you already know. We're going to set up the dot product here with a numpy dot product between A and B. And then we're going to use our linear algebra to set up our vector A. And then we're going to set up our vector B as well with our linear algebra. And we're going to calculate the cosine as the dot product divided by our vectors here multiplied with one another. And then we're going to print our cosine. And from our cosine, then we can derive our angle. To derive our angle, we set up our angle in radians with the math and the a cosine, the arc cosine function for this cosine here. And then we convert our angle in radians to degrees. And for that, then we're seeing our cosine is this here. Our angle in radians is this, and our angle in degrees is 19.1. All right, straight up program math. Is it fun? It probably is, but you know what? We can do this much more easily by just saying, give me the cosine similarity between vectors A and vectors B. Oh, wow. Well, that is an interesting error, isn't it? Let's see what it tells us. Obviously, our cosine similarity, vector A, vector B, that's where the error occurred because we're seeing this with the arrow here. And the problem is expected a 2D array got a 1D array, D for dimension, two-dimensional array got a one-dimensional array instead, and reshape your data either using array.reshape if, okay, your data has a single feature, or array.reshape 1 minus 1 if it contains a single sample. So what this tells me is I need to reshape something, which means my data is in the wrong format. Oh, I probably did not pre-process my data correctly, right? So reshaping, in fact, is part of pre-processing. So let's try this again. We are going to reshape our data because our data contains a single sample. Yeah, because this here is a single sample, right? This is another single sample. So now we need to actually align our arrays. Let's do that. So I'm going to call my first array, instead of A, I'm going to call it A, and I'm going to use reshape for my array A here. And I'm going to say reshape 1 because we had a single sample, but we have 3 items, 3 values in our array because look here, 1, 2, 3, right? And I'm going to have to do the same thing for my array number B because I also have 1, 2, 3 samples in there. So I'm going to say, well, AA equals A.reshape 1, 3 because of the 3 values, right? And then BA is going to be my array B that's reshaped 1 and 3. So then I can calculate my cosine similarity between my reshaped AA and my reshaped BA arrays. And I can then apply my angle in radians with the arc cosine here, just in the same way in which I'm doing this here, and my degrees, derive my degrees from the angle in radians. All right, let's do that. And as you can see, here is my cosine based on the reshaped angles. Let's compare that with the cosine that we have calculated with the dot product before here. And not surprisingly, it's the same number, right? And then we have the angle in radians, which not surprisingly is also the same number as up here because we're using the same formula and we have the same cosine. And then we have the degrees right here. So that is our cosine similarity calculated, which is faster here certainly than our dot product calculation. All right, so now let's apply that again to the adult data set. And we're going to do exactly the same thing. First, we're going to have to convert our adult age and our adult income USD attributes to arrays likewise. And then here I'm going to use the dot product to manually compute my cosine similarity. So I'm going to use exactly the same process, generating the dot product between the two vectors here and using the linear algebra norm function applied to each one of my vectors with that gives me the cosine here between the dot product divided by each vector multiplied by one another. And then this is my cosine. I'm going to ask you here to compute the angle in degrees from this value here. And the way that you would do this is to apply the angle in radians and the degrees. And then I'm going to ask you to use sklearn metrics, which is this process to determine the cosine similarity, not between age and income USD, but between education years and income USD, as we did before. And then again, the idea is to determine which angle is smaller, because when the angle is smaller, it means that the two attributes that you are comparing are closer to one another. So it will be it will be possible for you to determine whether age and income USD are more closely related than education years and income USD, or vice versa. So that was a lot of math, or trigonometry, wasn't it? We first looked at the hypotenuse in our triangle as the Euclidean distance. Then we looked at the sides of the triangle with our Manhattan distance. And then finally, we looked at the angles of our triangle when we calculated cosine similarity. Well, are we done with the math? Well, maybe. We're done with that kind of math, with the trigonometry, and now we're going to switch gears and we're going to talk a little bit about not numbers, but about categorical attributes, because certainly we've learned how to transform categories into numbers, but at the same time, does it always make sense? And can we actually treat categorical attributes as attributes that we can compare? And the answer to that is yes, we can. But to do so, we need our chi-square algorithm. Chi-square calculates the relationship between observed and expected values, but for that we need two categorical attributes. So basically here we are looking at things like small, medium, large, extra large as categories, and then we're looking at the differences between the expected values, here shown in yellow, and the observed values. All right, so since we're not necessarily working with numbers, we're going to have to work with a different kind of math. That different kind of math is called hypothesis testing. So you may remember that all hypothesis testing starts by setting up a null hypothesis, often called H-null, and an alternative hypothesis, often also called HA. The null hypothesis starts by assuming that the two variables you're comparing are either dependent or independent or equal, depending on what math follows. For chi-square, the H-null is always that the two attributes that we're comparing are independent, as in not related to one another. The alternative hypothesis would then be that the two attributes that we're comparing are in fact dependent or related to one another. How can we determine the difference? We are going to look at the p-value that results from our chi-square calculation. If the p-value as a result of our chi-square calculation is greater than 0.05, which is 5%, then the H-null, our null hypothesis, is most likely true, meaning that the two attributes that we're comparing are independent. If it is less than 0.05, that's less than 5%, then we cannot prove that our null hypothesis is true, and the alternative hypothesis is more likely to be true. So for that, again, the p-value plays the most important important role. And as a fun and very nerdy side note and example, check out the chi-square calculation that relates the uniform color in Star Trek to whether or not someone is going to die in an episode. That's right here as the chi-square test of independence with this example and a great explanation. All right, so you may remember chi-square as involving a table in which you look up different kinds of values, etc. In programming, we don't need to do all that. All we need is our SciPy stats chi-square contingency function. This automatically computes the expected values from the chi-square table that you used to have to use. You don't have to do that anymore. And it spits out the output with 4 variables: the chi-square number, the p-value, the degrees of freedom, and the array itself. And the thing we're most interested in is, of course, the p-value, because the p-value allows us to determine whether our H null has been proven, meaning if the p-value is greater than 0.05, our H null is most likely true, that the two attributes are independent from one another, or if our p-value that comes out is less than 0.05, it means that our H null cannot be proven and that instead we can assume that our alternative hypothesis is more likely true. The math is very elegant here, and we can solve everything in one line here. We start by relating our two categorical attributes. I've selected native country and occupation here because they're both categorical and non-numeric. We are going to relate them with the pandas crosstab as a cross-tabulation function. We're going to cross-tabulate their values. And to this cross-tabulation, we're going to apply the chi2 contingency function. Once we have done that, we can pull out from that the chi-square statistic, the p-value, the degrees of freedom, any expected values, and so on. Here, we're going to take a look at the chi-square statistic itself as chi2. We're going to look at the p-value, and we're going to look at the degrees of freedom because we can, but really our focus is going to be the p-value. So let's do that. And what we're seeing here is a p-value of, hey, 3.05600. That's a really large p-value, but oh, wait. It ends with E minus 227. What does that mean? Whenever you see an E at the end of this number, it means 10 to the power of what comes behind it. 10 to the power of minus 227 is in fact a very, very small number. So we are multiplying 3.056 and so on times 10 to the power of minus 227. That is a very small number. It certainly is smaller than the 0.05 that is our measuring stick here. Because remember, if the resulting p-value is greater than 0.05, both variables are independent, meaning that our variables of native country and adult occupation would be independent from one another. Now our outcome shows us that the resulting p-value is much smaller than 0.05, so our variables are in fact dependent on one another. So now I'm challenging you to calculate the chi-square relationship between sex and occupation in the adult data set, and to tell me whether the occupational status is dependent on or independent from the person's sex. Our final topic in our measures of association in this workbook is covariance and correlation. Covariance and correlation are connected. The goal for both of these calculations is to determine if two variables are tightly enough connected that we can detect a pattern to their changes. So we want to find out if when one variable changes, the other variable changes as well. If A grows, does B grow, or does B get smaller? And can we predict those changes in some way? I encourage you to take a look at the instructor video here in order to find out more about covariance and correlation. First things first, since covariance and also correlation rely on numeric calculations, we have to use numeric attributes for them. We cannot use categorical attributes. That's why we have chi-square. So in our case here, I'm going to work with income USD and education years. There are two types of covariance, namely sample covariance and population covariance, that work on either sample or, well, population. To get the sample covariance, which is the default setting, the degrees of freedom are set to 1. To get the population covariance, we are setting the degrees of freedom to 0. In our case, it really doesn't matter because we are getting very, very similar results, as you can tell with np.cov and here between education years and income USD. We can also achieve the same thing with our bias setting here. If we set our bias to true, that gives us the population covariance. If we omit the bias true setting, that gives us our sample covariance. And again, our values are not that much different from one another. But what's much more interesting is what these numbers actually mean that we're getting here. So the way we read our results is that if our education years increases by 1, then the income USD is calculated to increase by 33,078. So if education years only increases by 1, then we see this change here in our income USD. All right, so I'm asking you here to calculate the covariance between age and income USD for the population. Remember to use the correct bias setting and then determine how much the income increases or decreases if age increases by 1. Correlation is essentially almost the same as covariance, but it is normalized, meaning that the numeric ranges of both attributes are on the same scale. This produces the Pearson correlation coefficient. This Pearson correlation coefficient falls on a range between -1 and +1 and is commonly abbreviated with R. So if you see an R value between two attributes here, X and Y, that is negative, that means as our X value grows, our Y value falls. This produces an inverse correlation or a negative correlation. If our R value is somewhere around 0, it means really that there is no relationship that we can detect between our X values and our Y values. And if our R value is positive, as in here, it means that we can detect a positive correlation between our X value and our Y values, meaning as our X grows, our Y grows as well. A perfect negative correlation means that our R value is -1, and a perfect positive correlation will set our R value to +1. Calculating correlation is one of the most frequent activities in data science and in business analytics. And here is how you do that. So let's go back to our education years on our income USD. In order to calculate our correlation, all we do is we say, let's take our adult education years here in the square bracket again, dot, and then we're going to correlate that dot core to our adult income USD. And that will then produce our correlation. Here we're seeing a 0.28 positive correlation. So it's slightly positive, which means we can assume that there is a good chance that education years and income USD are correlated and grow together. We can also plot this with PyPlot and produce a scatter plot here. That's what you're seeing here. But the real power of the core function, the correlation function, lies in its ability to handle multiple attributes or multiple dimensions at the same time. So if we just write adult.core without correlating expressly to specific attributes, then it will produce a correlation table. That's what you're seeing here. And we're seeing that, of course, the attributes when correlated to themselves will always produce a perfect correlation here. Age to age is always 1. Education years to education years is always 1. But what's really interesting is to see the correlation between education years and age, hours per week and age, income USD and age, and so on and so on. And this always happens only, of course, for the numeric attributes. And here, when we scan this table, we can see that the highest correlation that we're finding is between income USD and education years. And of course, the reverse is also true, between education years and income USD at 0.28. And that's what we saw up here as well. One of the cool things that we can do with these colors is we can plot them in a heat map. So using the cool warm colors, we see here in this heat map that the perfect positive correlations are dark red, the perfect negative correlations are dark blue, and everything else is in between. So what we're seeing here right away is that all the correlations fall into the positive side here. Some of them are a little bit darker, that is a bit more positively correlated, more strongly positively correlated than others. That gives us a really quick, really good visual. And remember, in business, a quick picture says more than 1,000 words. So this is something really useful if you are ever in a business situation. Having said that, the Pearson correlation coefficient is not the only correlation coefficient. It is, however, the most frequently used one. The core function supports other correlation coefficients as well, such as the Spearman-Rho correlation, which I encourage you to research on your own. So now, go ahead and practice this. Practice calculating the covariance between hours per week and income USD, and also the correlation between hours per week and income USD. And then see if you can explain how these two numbers are related. Once you've done that, you have completed all the work for this workbook, which we started by talking about distance as a measure of association, specifically Euclidean, Manhattan cosine similarity. Then we moved into categorical attributes and chi-square. And then we moved back to numeric attributes with covariance and correlation. Thank you very much, and I look forward to seeing you again in a future video.